You're good to go.
Just minimize this one, right?
You can actually tell.
Should I
the video here.
do I have to do that start
Yeah.
broadcast?
Start broadcast.
Start broadcast. Start broadcast. Thought we did it already.
Yeah, I did that already. I don't know why it came again.
All right. Okay. So today I'm going to be talking about transient tropical ocean atmosphere response to anthropogenic sulfate aerosols. So the outline of the talk is as follows. So the first few slides will be the introduction, followed by a main question. Then I'll go on and talk a little bit about how I'm trying to answer that question by showing you the model and experiment details. And the final, it's results and conclusions, which are divided into 3 parts. Starts with the broad results, and then we're going to focus on the tropical ocean feedback response, which is the meat of this talk. And then a couple of slides are about just few new results. So let's start with the introduction. So what you see here in this figure is annual mean radiative forcing, which was calculated using this particular model. And what you're seeing here is a radiative forcing for sulfate aerosols, for biomass burning, for black carbon aerosol, and it's compared to when you double the carbon dioxide from its pre-industrial, from 1860 carbon dioxide, what happens. So one clear difference, what you can see here is, so all of these aerosols radiative forcing, they are much more non-uniform. They have a lot of regional character to it in comparison to what you see for the carbon dioxide. So also for the benefit of everybody, so just as how do you define a radiative forcing? In simple terms, what a radiative forcing is, it's a variable which tells you the excess or deficit of energy which is coming into the climate system, whether it is excess or deficit of what on an equilibrium climate condition it should be. So as you can see in the sulfate aerosols, you would see the cooler color means here there is a deficit of energy into the climate system over these regions, right over this region. If you compare it to the black carbon, it shows mostly the warm colors, which how it should be. The biomass burning also, you see it has mixed character both, and the carbon dioxide is mostly warming. That's what you see here.
The unit is in watts per meter square.
This is watts per meter square, and
So
this
the
is this.
The local cooling can be on the order of 10 watts.
Yes, and so the thing is, what you have to remember here is this radiative forcing quantity is not yet fully constrained. Like different models have their own variations, but this is how it is. So that's the radiative forcing. So it is a perturbation into the system. And the next slide shows the response. So this is not actually SST. This is the surface air temperature, what you see here. There's a mistake there. And this is the climate response. This is the annual mean surface air temperature response. The top one is for the sulfates, and this is for the black carbons. And as you would expect, since there is a deficit of energy, you see a similar cooling over almost all over the planet. So one thing to keep in mind is the radiative forcing is the perturbation into the system. So it's not, the way they calculate radiative forcing is they do not have a coupled model, and they don't allow the climate feedbacks and other things to happen. It's only calculated, it's only the perturbation. So it's local, but the response is global, as you can see. So this is the surface air temperature from the same paper. There's another paper by Oko et al. In 2014. It's a different model, And what they're showing here is the sea surface temperature response to sulfates, and this is to the black carbon. As you can see, even in the climate response, there is a lot of difference between the two different models. It looks like this particular model also has some regional warming in case of sulfates and regional cooling in case of black carbon, which was not evident in the Hadley Center model. Next, this is more on the regional response. So also, as you can see, in the case of sulfates, the northern hemisphere warms stronger than northern hemisphere cools, whereas the southern hemisphere doesn't cool as much as it should be.
So which model is those guys?
This is the GFDLs.
This is GFDL model?
This is GFDL. This is the older generation of Hadley Center model, and this one is not. This is using a full coupled mode. This is only using a mixed layer mode.
Oh, that could explain though. I mean,
that could also explain.
That thing seemed to me looks like an AMOC response.
Yes, that is from the mixed layer model. Yes, I think I think that's right. So what you're seeing in this figure is, let's start from here. So during the late 20th century, roughly from a period of 1960s to 1980s, there was a lot of droughts along this belt in the tropics. And so a lot of people have studied that in past. A lot of people have come up with reasons like the drought in this particular band to be related to the ocean variability. And I think in our group also we have a paper which talks about the ocean, the role of ocean in the Sahel drying period. But what this paper by Hwang et al. In 2013, they've come up with another mechanism which says that it's probably due to the sulfate aerosols. So during that period, during 1960 to 1980s, there was also an increase in sulfate aerosols. And the way what they're showing here is they're showing this is a precipitation difference between these two periods, between this period minus this period. And what you're seeing here is the warmer color here means it's drying, so that don't confuse it with that. And the bluer color means it's becoming more wet. So this is from a GHCN, which is a gridded product from a land rainfall station, measuring stations. This is from a 20th century analysis, and this is from an ensemble of GCMs from CMIP3 and CMIP5. And essentially this is the zonal mean averages of what you're seeing here. So as you can see, there is a drying in this part, there is a wet, it's becoming more wet. You see this southward shift of ITCZ in all these evidence, though the finer details are different. And essentially the mechanism, what they said, is essentially this. So what you do is when you have more sulfates in the northern hemisphere, so northern hemisphere becomes colder than what it should be in its equilibrium conditions. And because of that, there is an anomalous Hadley circulation which sets up, which tries to transfer the energy from the southern hemisphere to the northern hemisphere in order to balance that energy deficit in the northern hemisphere. Whereas on the lower side of the anomalous Hadley circulation, there is a lot of moisture which gets transferred south, and essentially you have a rain band which moves south. And essentially what they said is that this cooling which was locally introduced, the eddies take it around and spread it all over in the northern hemisphere. So that's their mechanism. Another application of sulfates, especially when we're talking about volcanic aerosols. We know volcanoes emit a lot of volcanic ash, which is just nothing but pulverized minerals and rocks. And in addition to that, it also adds a lot of sulfur dioxide and hydrogen sulfide into the atmosphere. Now, if the eruption is strong enough that sulfur dioxide and the volcanic ash, it can also enter the stratosphere, where it stays for much longer. It can even stay up to almost 5 to 6 years. But the less strong eruptions, it means this doesn't happen with all the volcanic eruptions. It only happens when you have very strong volcanic eruptions. It can enter stratosphere. So essentially what people have tried to do is, of course, you cannot control when the volcanoes and where will it emit, but once it's been erupted, you can use this fact and do some decadal predictions or a longer term predictability essentially. So what you're seeing here, this is from a paper from Collins in 2003. And what they've done is they have done some retrospective predictions using this particular model for a Pinatubo eruption. So the figure here, what you see here is the solid line is the ensemble mean, the dashed thick line is the observation, and the rest of the gray lines are the ensemble means. And this particular line, vertical line, is the eruption, when the eruption has happened. So what they've done is, so they've taken a PDF, so that the gray PDF is the climatological PDF for the DJF following the eruption, and this is for the JJA following the eruption. And the other PDF, just the line of a PDF, is the change, is the new PDF, which they constructed from all these retrospective predictions. So essentially, what they're saying here is, so we gain some predictability in the winter next after the eruption and the summer after the eruption, just because you have emitted a lot of sulfates into the stratosphere, and they essentially block the incoming solar radiation, and therefore cool the global mean surface air temperature, and which can be easily distinguished even in this PDF, and it can give you some predictability on this time scale. So that's almost a decade-old paper. Then there is a new study by Timrek et al. In 2016, the Max Planck group, and essentially what they've done is they're also going along a similar direction, but these guys have presented it slightly differently. So what I'm showing you here, so they use something called a Milkip prediction system. It's a coupled model system, and they do two sets of run. One is non-volcanic aerosols, and one is the reference aerosol. And what you're seeing here is the difference between non-volcanic aerosol minus reference. Again, these are hindcasts. And what you're seeing here is a correlation between the ensemble mean surface air temperature predicted by these two, predicted by the model versus the observation. So essentially what you're seeing here, the cooler color here means a decrease in the prediction skill, and the warmer color here means increase in prediction skill. So what they're saying here is when we take out the aerosols, you see and this is for the lead 1 year, this is for the lead 2.5 year, and essentially you can notice, if you just focus on this picture, you can see almost everywhere over tropics, you have a reduced prediction scale on 2 to 5 years when you take out the volcanic aerosols, but only over the eastern tropical Pacific you seem to gain some prediction skill. So which indirectly implies that the dynamics over this region, this eastern Pacific is a region where the temperature over this region is very much governed by the upper ocean dynamics. So essentially the implication from these two results is that there is a gain of prediction scale when you take out the aerosols, the volcanic aerosols. And what they say here is that it indirectly implies that the volcanic aerosols in the stratosphere, it does affect somewhere the dynamics, it does perturb it. It's some indication of it. So this is more for a global, this is on a regional scale. And now this is the last introduction slide. It's a schematic which essentially tells you the forcing and feedback pathways in the climate system. So essentially, let me just go through it. So you have aerosols and greenhouse, which are my anthropogenic sources. Then you have a radiation, you have also clouds. And in the end, these are the responses. These are the global surface temperature and certain atmospheric variables, which are the responses. And this goes as follows. So let's start with the aerosols. So let's say you have added aerosols to it. Now it has aerosol radiation interaction as well as aerosol cloud interaction. Once that is done, once immediately this happens, then there is a lot of rapid adjustments. This radiation interacts with the local variables, the local moisture and winds temperature profile, which also rapidly adjusts the clouds here. And then this loop is called a rapid adjustment. Once this is done, then you get some transient climate response once happens. And once the transient climate response happens, you also have some feedbacks from the surface temperature, which could be air temperature or ocean temperature, which feedbacks into the loop. And in the end, when all these things are settled, in the end, you get an equilibrium climate response. Just one main point here, the rapid adjustments are not same as climate feedbacks. Rapid adjustments happen on much faster time scale, where the climate feedbacks has to go through the ocean or the surface temperature. That's the main difference in the framework. Okay, so that's the introduction. Now, this is the question which I want to answer in this talk, which is, does regional climate response to anthropogenic sulfate aerosols over Southeast Asia excite ocean feedback response over tropical Pacific? That's the thing what we were trying to answer. So in order to answer that, I'm doing it with the help of a modeling study. Here my model and experimental details. I'm using CASM version 1.1.2. I'm using both it in fully as well as partially coupled framework. These are the other details. And the approach taken is as follows. So I have one long control case, which it almost extends, right now it extends almost up to 110 years. And for this control case, all the forcings are set from pre-industrial time, all the sulfates as well as all the other forcing that needed itself set from the pre-industrial time. And the perturbed case is every January from this control, I pick an initial condition and start another run. But in this case, I've changed the emissions of sulfates from pre-industrial level to the 2000 level. And I run it not just for 1 year, but I run it for 2 years. So if I make a difference between the brown line and the blue line in the end on an ensemble mean, it can give you a first 2 years of a response to sulfate aerosols. So let's look at some results. So let me start with showing you the response in the aerosol optical depth in a visible band. So what you see here is JFM, AMJ, JS, and OND. These are the successive 3 months averages starting from the January. And so aerosol optical depth is essentially, it's a measure of how aerosols are reacting with radiation. On an average, the negative of this number is proportional to on an average, the transmittivity of atmospheric column. So if there is a positive AOD change, that means it's blocking some of the shortwave energy, or in this case, it's just a visible band. So there are a few things what you can make that there is definitely a seasonality. There is definitely a seasonality. As you can see, it's much more in AMJ, JAS if you compare it with OND and JFM. And the maximas are the regions where most of these sulfates and its precursor gases are emitted. And there are 2 blocks I'm showing here. I'm calling this a local region and I'm calling this a remote region. And I'll just show how this response evolves from 1st January. This is the first year and this is the second year. So let's just concentrate on the solid line. So the green line is how this response evolves initially from the first month. And you can clearly see a seasonal cycle. And the local response is shown in the blue. And there also you see a seasonal cycle. But there are 2 very clear things what you can see. First thing is locally the response is greater. Remote response is smaller. As you can see, the mean is smaller. And the spread in this essentially is the first standard deviation. So what you can see here is there is a lot of spread from year to year. How much of a AOD change in particular month is that it has a lot of variability in it. But the point I'm trying to make here is it does. So if you consider the variability, I can safely assume that the aerosol radiation interaction or aerosol optical depth is same between the first and the second year. So that's the aerosol radiation interaction. Now let's look at the STI response, which is what we are mostly interested in. It's again in the same format. So it's the first 3 months, after that, and after that. So as you would see here, let's look at first only the cooling response. In the first few months, in January, February, March, there is a small response which is very local to where most of the forcing is. and then it spreads out. It becomes stronger. It becomes strongest in the summer season, and it again starting to die down here. But in addition, so you can see that there is also a seasonality in the cooling response. But in addition to the cooling response, you can also see that in the tropics there is also a warming response, which instead of peaking in a summer season, it kind of peaks in October, November, December. So this is for the first year. You could continue it for the second year. Now in second year, what happens is you already have some cooling. Now the sea surface, now obviously the ocean has inertia, so the cooling continues. It becomes stronger and it becomes more pronounced, and it also spreads everywhere. It also reaches closer to the equator, and in this case, it even goes along this SPCZ band. And you can also see that the response in the tropical Pacific response, which started out like this, it's becoming weaker. And again, this is the second set of response which is picked up in the second year. So it's not the same response, and at least in the SST, it's not the same response, but it looks like two different responses which peaks during that season. So that's the sea surface temperature response. Now, these are the two figures which I've already shown you. Now I'm showing you only the AOD response in summer and winter. And this is, again, the SST response in summer and winter only of the first year. Now, what you can see here is my aerosol radiation interaction seems to be largest over the land regions, but my SST response seems to be greatest in the remote regions. So what that tells you is that this alone cannot explain how my sea surface temperature response. If you just look at the cooling, my cooling is strongest over the North Pacific, whereas my AOD response was strongest over the lands. So which tells us that there is something else happening here. And now what I'm showing you here is the shortwave cloud radiative forcing. And it's obviously it's positive downwards. So the blue color here means now because of the change in the cloud structure, the incoming shortwave energy is reduced. That's why you have cooling almost all over. And this kind of explains that why you have the biggest response in SST over this region, rather than means it explains that part. So it's now this cloud. I'm just calling it a cloud effect. I'm not still calling it aerosol cloud interaction, because the change in cloud is not just tied to how the aerosols affect the cloud, but it also could be some cloud SST feedbacks which changes the cloud structure, and you get this response. So this essentially is the broad picture what I was talking about. So essentially we learned three things here. The aerosol depth, from aerosol optical depth change, we know that it exhibits a seasonality which is strongest in the northern hemisphere summer. So I haven't shown you this, but this also is seen. And there is no appreciable change between first and second year. In the SST response, there is a cooling over most of the northern hemisphere, which peaks during summer. There's a warming over tropical Pacific, which peaks during winter, which is the meat for this, what we're going to analyze in a little more detail. And also, what I also wanted to bring about that, of course, though we are changing the aerosols, which in turn change the SST, but SST changes are more slower. So SST has a seasonal as well as a slower trend response in it, which itself can force back into the atmosphere. So if you analyze any of the atmospheric variable, there's a good chance that you might see a slower trend which might be coming from the SST response, and the seasonality which could be because of the both. And essentially this is what I was talking before, that the shortwave cloud radiative forcing tells that there is some indication of aerosol cloud interaction and or other cloud related feedbacks.
So for this SST response, the Pacific SST response, so the way you did this experiment, you basically have 100 years control, right? And then you take average annual, right?
Start,
and then you do this 2 years integration. Right?
Yes.
So in this control simulation, it must be El Nino years versus La Nina years.
Yes.
Right? So did you actually look the evolution? I'm wondering whether that warming response you actually see happen during the evolution of El Nino, or it's actually happening in all the year. And I was wondering if you have
So I think now I have checked
subdivided
that thing,
Yeah.
but only thing is I haven't done it. I've done it when I had a relatively small sample, so I couldn't see anything.
So for each year, does the software aerosol forcing stays the same?
It stays the same.
So for all
That's what I was trying. That's what I was trying to.
all 2 years, it's the same forcing.
Yeah, it's the same forcing, and it's not as I showed. The AOD changes are not very different from first to second year. So even the aerosol radiation interaction is also kind of stays the same.
Well, plot earlier on, you have the line plots.
Oh yeah.
You have that. Only have only we have one for each year. Like right in the beginning, go back to the model.
Did I?
We have a plot like this for all the lines.
Oh yeah, I don't have it here. Means I have it online. I can.
But that lands the things all going up. It's only doing something.
Yeah, but it's. I think.
I mean, it might be interesting to see whether the thing, has a particular
So there are
on those years where there's El Nino going on in the Pacific, or maybe it has a less impact.
So I have done that analysis. I've done that analysis with when I had a shorter ensemble. We didn't see any correlation, but then there are two things. The way I did it is, I tried to regress it against a Nino 3.4 at the start of every January versus the response, the annual mean. So in that I didn't see anything, but I think maybe what we should do is we should also.
I think simply what you want to do is that you pick those years. Let's say the El Nino is developing, right, and then you calculate the amount of the warming you see in those years if you have enough sample.
Yeah.
And versus the years there's no El Nino at all.
Yeah.
And versus the year there's actually a La Nina going on. And that would give you something to see, which of this actually give you the stronger warming, because it's interesting to see. Could be that some of the thing, when you average out,
It should.
Thing,
Yeah.
it doesn't tell you what is really going on.
Yeah, I have done that analysis, but with the smaller sample, so I didn't see anything. I should do it when I have a bigger sample. No, I think I should do that.
And the other things I was going to ask you was that the software aerosol forcing was applied globally, right? It's not only from.
It's emission. So you're not. So the way the experiment is designed, you only change the emissions. Now emissions it happens. Yeah, it's globally, but it itself has its local character. Only few regions emit.
Right. I know that, but it's not only you're putting the.
No. It's everywhere.
In Asia.
No. It's
whenever there's data, you have to put it into there.
Yes.
In a realistic way.
Yes.
Okay.
Yes. So that's a broader picture. Now let's look at just the tropical Pacific warming. So what this plot shows you is on the top this is the annual mean SST response, and what you see here is this is the annual mean net heat flux at surface into the ocean. So as you can see, there is a negative anomaly of heat flux over this region, which is consistent with that we have a cooling of sea surface temperature. Over this box, over the tropics, however, the signal is not very clear. So what I've done is I have averaged over these two boxes and made an index of sea surface temperature, annual mean sea surface temperature, as well as annual mean net heat flux at surface, and made a correlation between that and the net heat flux. And in the darker color is the North Pacific response. So what essentially it tells, there is a positive correlation between SST response and the net heat flux into the ocean. So when you have a lesser net heat flux, negative net heat flux going into the ocean, you have lesser temperature. As you increase the net heat flux, the SST response also increases. But on the other hand, if you take a tropical Pacific, there is an inverse relation. So what it tells us is that though this part of the ocean is atmospherically forced, in this case, it looks like the response in this is the other way around. It's the ocean which is giving back. So what essentially it says here is, because of this warming, you have the flux change in that direction. It's not in the other way direction. So it tells us that the origin of this tropical Pacific warming is not directly from the top. It's not directly forced from the top, but it has to come somewhere from the subsurface.
So how did you do that? You take the equilibrium changes in SST in each case,
Annual mean changes.
and you mean, so, okay.
Annual mean.
And you mean, so you have 2 years, so.
I'm showing only for the first year.
For the first year,
Only for the first year.
okay.
Second year,
Essentially, you have 100 some years, right?
100 some years. So these are
And then you're correlating the change in the SST versus the change in the survey.
yes.
Might be useful to do a lead lag case. I mean, to see whether the flux, if the flux is really forcing SST, you should see the flux is leaving SST.
I can do that, but this I think these in which case? Which case? In this case it's too fast. I think.
Too fast. Well, I mean, the flux are changing really fast.
Yeah.
But then
I think the lag maybe is few months.
Just a
Right.
month. I think I've seen some indication.
Don't see much of
Yes. I've looked at that, and I think it's, as everyone said, it's 1 or 2 months at the max.
Yeah, but it's nice to show that it is.
Okay. Okay.
Because simultaneous correlating, the problem that it's really tricky to diagnose the relationship between the SST and flux, because the flux is a function of SST always. So you have to be right.
I'll do. Yeah, but only thing is I do not have. Yeah, I can do that, but I don't have a lot of degree of freedom because I have only 12 or right now 24 months.
I think what might be just making a composite of the first year of flux change versus SST change in that region.
Where? The composite.
Yeah, just averaging all the 100 years, right? The first year of flux versus the first year SST change.
Oh, you want a line plot?
Yeah.
Yeah. Okay. I can do that.
And then from that we should see it.
I can do that. Do that.
I think.
But I think I've seen some indication in some.
And then if you do the similar plots in the tropics, then if the flux is damping the SST, then you should see SST change first, and then the flux changing later, right?
But I still believe that response is very small. Actually, that response is not that big.
The flux, the response in SST, or the response in
the response of the fluxes because of the change in SST.
Yeah, the other thing is that if you look at different components, I suspect that in isotropic is basically the short wave, which is
it's the short wave. It's the short wave. It's the incoming short wave.
Right.
And this is
the tropics is maybe the turbulence component. If it is responding to the SST.
There's a slight latent heat. Latent heat, yeah. Yeah. So anyway, I think hopefully I convinced you that this is not coming from the top, but it is coming from the under the ocean. So
how about the signal in the Indian Ocean? Isn't there something in the Indian Ocean that's pretty large?
You mean in the heat flux?
No, in the southern Indian Ocean.
Right here?
Right.
Yeah, that is. I think that is probably a latent heat flux.
And there's no SST signals corresponding to it.
Yeah, I actually don't know. No, it can't be SST obviously then. I have a split of it, but not right now. But I do know that over this region there is some convection activity also. Yeah, I didn't pay attention to Indian Ocean, but yes, could look at that. Okay, so let's look at then the upper ocean. So what I'm showing here is this is a temperature profile, which is a response again. So everything, all the figures are the response. So temperature profile along an equator. This is the West Pacific, this is the East Pacific, and as we see that there is some warming, there is a warming maxima around this depth. And so what we can also do is we can also look at response, the spatial response in the temperature, the ocean temperature at 105 meter depth. And I'm showing it for 2 seasons, for JAS and October, November, December. And you can see that there is a significant response even in this region, which becomes stronger from this to that.
This is the first year.
This is all the first year. I do have a second year. I can show you if you're interested.
You have the Hoffman.
I have the Hawmuller too. I have the Hawmuller
This
too.
looks awful like an Enso signal to me.
It is. It's okay. And even to take it further, you can also see a consistent response in the zonal currents. And so that's the upper ocean response. And then now I'm going to show next. I'm going to show the wind response. So here is the 850 hectopascal wind response. So what you're seeing here is, again, it's the same split, January, February, March, and it goes through October, November, December of first year. And the shaded regions are the regions where this response is significant, means it passes the test. And there is, particularly during this pre-monsoon season, you have a significant response. Its first thing is it's kind of always a westerly response, but it's kind of the most significant during this month. And it's only located over this region. And I'll show you a corresponding SST response. So you can see that let's just focus on the tropics. So there is nothing this month, there's nothing in this month, and it picks up in the JAS, and it becomes stronger during the October, November, December. So there is some correspondence between what's happening to the winds and what's happening to the sea surface temperature. And we know from the ENSO theory that the westerly wind response in the Western Pacific can trigger El Nino-like response in the tropical ocean.
Did you look the summer fine response?
Yes, I have.
You can make the same plot.
I have. I can show it.
This is the first year, right?
This is the first year. Now I'll show you the second year. This is in the second year. Of course, your second year, even your wind response picks up. And one thing to note here is it's not very significant during the transition months, but again, during AMJ, it kind of picks up. And then it stays there, and it also kind of moves in the Eastern Pacific, moves towards the Eastern Pacific. And so is the SST. So I think this is a remnant from the previous year. It dies down, and then again picks up, and it becomes stronger. And this time it is also shifted east. So the warming in the second year is also shifted east. So before I go further, let me also show, I have a similar plot for the subsurface.
Actually, the Atlantic looks interesting.
Yes, oh yeah, I forgot to mention that during this summer season, there is an Atlantic response. It's also in the first year response. It also shows up in the first year response, and it's a seasonal response. And not just that, actually, even if you go back a few slides, it also shows up in all the other variables I showed. Let me show this one. It also shows up in, so this is the same SST response in JAS. It shows up in the aerosol optical depth, as well as it shows up in a cloud forcing. So it's all connected. It's something interesting we could look at. Just switching back. This is the subsurface response. This is for all the 2 years. This is the subsurface response. These figures I have shown you before, but you can also see that not just that, there is also other things. There's a cooling propagating down here. There's a cooling propagating eastward, and all those things. So there's a lot of interesting response. So the point I'm trying to make here is
Now make me wondering if you integrate a longer, where the signal is going to go even stronger.
So I have, okay, since you brought it up, I can, so Weichun has done an equilibrium run.
Right.
And I think that was the starting point why we started looking in this, because we saw some warming in the equatorial Pacific. Right. And
But you also have the middle latitude cooling is propagating.
it is also equating, it's also propagating equatorward, not just on the surface, but even in, you can, Yeah. But since you brought it up, let me just also show that. It's the other way around.
So you're using the same model as Wei-Ting used, right?
It's the same model, yes. This is her equilibrium run on this one. This is her long-term response in SST, and there is some response which is more east and slightly south. So I think this was what we started out with because we wanted to know why this warming is
This
there.
is not a seasonal, this is the year.
This is an annual mean. This is an annual mean, but I haven't done seasonal, but I think it might show up even in that. Okay. So I've shown you this. Now let's, what I'm going to do is I'm going to do a Hofmolar plot along the west in the equatorial Pacific, and which looks like this. And I'm showing you two things. I'm showing a wind stress, I'm showing you a temperature, subsurface temperature, and I'm showing you SST. This is the West Pacific, this is the East Pacific, and the time goes this way. So it's the start of the run, and this is the end of the two runs. And as you can see, first, as you can see that this is the westerly wind stress, which was in the April, May, June on the Western Pacific. And after that, you can also see that there is some response developing in the subsurface ocean. And after that, even you can see that it's also developing in sea surface temperature. So it seems like that we are on a right track. It's the westerly wind stress here, which gives rise to this, the equatorial dynamical response, and which shows up in SST. And then again in the second year, again there is another blob of SST which shows in second year. You have a corresponding warming in the subsurface, and also you have a corresponding westerly wind stress around the same month, but then it kind of stays the same and it moves. So it's all very consistent, what you're seeing there.
And the shaded is significant.
Shaded is the 90 percentile.
90 or 95?
90. 90, but I think I'll increase it more. Only thing is, okay, so only thing is I've tweaked a bit. So these are 90, everything else is, whatever shown is all 90%. In the tropics, in the extratropics is 95% because it's even 99, it's anything shows up there. But only in SST, it's 85 right now. But we want to make it, I shouldn't have put this, but
You showed me and I said, nobody uses 85.
no, I just wanted to show because I've been showing for too long, I've been showing no significance at all.
So you just want to change.
I wanted to, show that yes, no, we are heading in the right direction. So this is for the fully coupled model, but the same plot I will show you for also the slab ocean model, where of course you won't have this middle panel.
I mean, you don't get a response during the late spring and early summer. It's not surprising. I mean, that's what is known as the spring barrier problem, right? So you don't get much of that.
I think it's very much it's somehow this it's essentially when you introduce sulfates, it somehow has that local cooling effect, and which kind of projects into the ENSO mechanism for a bit.
Actually cooling in East Asia.
Cooling in East Asia, which projects on this. Yeah. And
Seems to make sense to me.
And then this is the same wind stress, the zonal wind stress, and the sea surface temperature for slab ocean model. And as you can see, of course, you won't have all those tropical Pacific warming because you don't have this mechanism coming from subsurface. So, but what you see here is you do see a response even in the same month in the wind stress, the westerly wind stress, and then of course it's all cooling after that. That's the typical just how it's equilibrating. I think this response is your on the Western Pacific. It just progresses, and also it's coming from the top. It's coming from the North Pacific. Also, it's going down as well as it's progressing from the West Pacific.
In a slab ocean, do you see the similar thing in the Atlantic Ocean? pattern, the seasonal pattern, evolution pattern that
You mean, no, it adjusts very quick. I have a figure. It adjusts very quickly. It's very strong. I'll show you the SST. It adjusts very quickly. It just, after that, it's everywhere warm, cold. Just. It's hard to see a seasonality in this, but it's too strong a trend. Okay. So that's mostly the end of that, except I have one more slide from that. So what you could do is you could also look at the Bjerknes feedback kind of a mechanism where it tells that it's the weakening easterlies which leads to the flow of warm water in a layer above thermocline towards east, deepening of thermocline, and then there is a less cold equatorial upwelling, and then which leads to the warming of SST. In our situation, we can also, I think I should have put the same way, but what I'm trying to say here is in this case, it's equivalent to a Western Pacific westerly wind stress, which leads to Eastern Pacific subsurface warming, which leads to Eastern Pacific warm SST, and it kind of, if it's that way, it should complete the loop. So what I've done is I've done a cross correlation between this, between them, which is shown here. The first figure is essentially this cross correlation between westerly wind stress and the subsurface temperature. So what you're seeing here is, so over this box, you can create an index of a westerly wind stress over this index, and then you can correlate it with the temperature everywhere. Am I making sense?
So the stress, this is again using the annual mean.
This is using an annual mean, but I'll also show you during October, November, December.
But this figure is constructed using the annual mean.
This is using annual mean.
Okay, so you construct the annual mean anomaly index for the wind stress.
Yes, and you correlate
correlating to the SST.
Not
annual
SST.
mean.
This one is subsurface.
Right, the subsurface temperature anomaly.
Yes. So as you can see that the westerly wind stress over this region is positively correlated with the warming over the eastern side, and there is this seesaw of thing. The next one is the other link, which takes a subsurface warming on a subsurface temperature response over this region and correlates with the sea surface temperature above it. And this is also as you would expect. If there's a warming below, there is a warming above, which is anti-correlated to what's happening on the western side of the coast. And the next one is the other loop, which is the sea surface temperature anomaly over this, the sea surface temperature response over this region. Now you correlate back to the zonal wind stress, which shows up here. So there are two interesting things actually you can get out of this. First thing is that the warming over this region is positively correlated to the wind stress over this region, westerly wind stress over the region, but it is directly over it is negatively correlated. So I'm not sure about, but I think the way I'm interpreting it is that probably this connection is not very strong. It's not strong enough. I could be wrong here because Saravanan thinks that annual mean could be giving you a wrong thing. You should do it differently. But and also he was mentioning that it's probably not SST, it's probably the SST gradients which are important. But what I'm trying to say here is because this loop doesn't complete, that's why your warming doesn't indefinitely go on increasing as you're progressing. It kind of dies down because you don't have a very strong feedback into the system.
So you're calling it an SST. Let's see, if the SST is warming, then the anomaly should be, wind anomalies should be positive.
That's what I thought. In Bjerknes feedback, it has to be that way. Bjerknes feedback, it has to be that way. And if I do it the same thing for the...
So one thing you can check is that take the control simulation of the model.
And see how that responds.
How that actually, I mean, sometimes the model doesn't give you the right thing.
You're saying it could be a model deficiency?
It could be a model bias there. So what you do is say you take the model simulated at SST, right? And then do the same correlation just for the control simulation itself,
Okay.
right? So you should get a pattern.
Okay.
And the other thing is they probably want
Do again.
to take a particular season.
I'll show you. I have for the October, November, December when we have the greatest warming. And this is for the October. It doesn't change much. There are a few things changed. Like, okay, I should have put it in the, but this thing shows up. This becomes a little weaker. But more or less the patterns doesn't change. It's the same.
What if you do the temperature at the whatever the subsurface temperature correlating to the wind strength?
It's done one way, means you mean the other way around.
Just correlating instead of correlating and you use 3.4 SST to correlate the subsurface temperature back to the wind strength.
I can do that.
And to see what kind of pattern you have.
Yeah. It's only one. In this case, it's just a one way, but that's should be. All right. So this is a summary of this particular thing. So I'm saying that it is. There are 3 steps to it. There is a surface cooling over the Western Pacific, which is essentially because of all the clouds and the sulfates you have introduced into the system, which induces an anomalous zonal atmospheric circulation over that region. And in the 3rd step, it's the surface response, the westerly response is which kind of kicks in this particular response, and there is a warming in the subsurface which shows up here. Now, this is a summary, and only thing is when I'm saying that this particular, you should actually also think about, it could be that there is also the response in atmospheric circulation is not just SST driven. It could also be coming from above. Now in above, it could be 2 ways. It could be that there is just an elevated cooling, I have a precipitation response. Or also it could also be modified by the aerosol cloud interaction, because that itself reduces the precipitation to some extent.
Yeah, the other thing you can do is say instead of doing the correlation, you can do a composite, looking for those years where the SST anomaly is the strongest.
Okay, the SST response is strongest, and
Right. And then looking at a composite, taking all those years and compositing the warming pattern to the wind.
okay, or we could just do a regression.
Well, the regression, then you're gonna take all the wake ones too, right?
Yeah. Okay.
You're gonna weaken the signal.
Okay.
But if you just do the composite, at least you can see whether.
Okay.
And it'd be really interesting to see what are those that stronger years, and what make those years so strong.
Yeah.
And it's the
I somehow feel that it, as you are saying, it might depend on.
Depends on the background.
It might depend on whether it's.
So in other words, it could be reinforced. If you already have ENSO on the development,
Yeah.
it may accelerate its development, right?
Yeah, it means even I was also thinking about it, and I think I was also, I think I should look at this. I think I should probably look at AMJ.
Yeah.
At that,
You can just that's easy to do. Just check to see, if those are strong events you actually see corresponds to any background.
Okay.
Kind of background.
Yeah, I think I should do that. And just to end with, these are some newer results. I won't go too much into detail, but there's one catch here, which is as follows. So this is the precipitation response, annual mean precipitation response. So a big reduction of precipitation over this region. But this precipitation, actually, if you look, this is a convective precipitation. It comes from a cumulus parametrization. Now, cumulus parametrization is usually thought to be connected to a deep convection. But if you look at a high cloud fraction, which is the macrophysical quantity, which tells you how much of a cloud amount is present, it tells you that it actually increases over a similar region. If you look at over this particular region, it kind of increases where you have a reduction in precipitation. So which is a little counterintuitive, because typically if you have a reduction in precipitation, the cloud cover also should go according to that. Now this, what you could also do is you could also look at some microphysical quantities, which are the two quantities called effective radius of a cloud droplet, and the other one is the number concentration of a cloud ice, because I'm averaging over the upper part of the atmosphere, upper part of troposphere, from 250 millibars to 100 millibar. So the colors here are the change in the effective radius, which very much looks like a precipitation response. There's a reduction in effective radius, as you would expect, in tune with the precipitation. And the contour here, it tells the region where there is an increase in the cloud ice. So this is leading us towards some kind of a aerosol cloud interaction. And essentially what it tells is, one way to, I think, I'm not very sure about it, but one way to think about it is the precipitation response is essentially through the cooling of sea surface temperature and the fluxes. But the cloud fraction response is coming from the microphysics, because the aerosols can directly affect the microphysics by changing, because when you have more sulfates, you have more CCNs into the count, into the atmosphere, which leads to the increase in the number concentration of cloud ice and also that decrease. So this is something new thing what I'm actually looking at.
And the units here, that's the cloud fraction, right?
Yeah, so it's unitless. It's just a fraction,
Just a percentage,
just a percentage.
6%.
Yes. So this is a little counterintuitive, but okay, the next one, what I'm showing you here is you can also look at something called a local Hadley and a Walker-Cell response. So you have omega, which is a vertical velocity. You can partition into two. Either the circulation is a meridional direction or is it in a zonal direction. And then if you multiply it with certain variables, you can get a mass flux. So in this case, what you see is a meridional mass flux at this sigma level 18, which is roughly around mid troposphere or mid atmosphere. And what I'm showing here is the October, November, December. And as you can see that this there is a decrease over this region, there is an increase over this region, which essentially shows some kind of a shift, what I was talking about initially, that my ITCZ is shifting south. But you can also do the same thing, but in the zonal direction, and which looks like this. And in this case, what is interesting is this particular region where you have a subsidence over this region. So essentially what it tells is that over this region, the response is in zonal, like this. Whereas over this region, it's the shift of the ITCZ. The response is such, which can be explained by the shift of ITCZ in October, November, December. You can also do these things, same things with a slab ocean model, which has a much stronger asymmetry between northern hemisphere and southern hemisphere, which looks like this. Of course, this response is much stronger. This response is present initially. The Walker-Cell response is present initially, but if I go further, this response won't be left anymore. If I go into the second year, the Walker-Cell response becomes much smaller, whereas this becomes.
Isn't that the arrow pointing to the wrong direction in a slab ocean?
Yeah, it's weird. So in essentially, I can think about it as this is the wind stress vector, which is very close to the. I don't know how they even compute wind stress in slab ocean model.
It's the same way.
It's the same way.
Yeah. Stress is computed.
Yeah, but yeah, it's that's how it is. I don't know how to explain that to you. Well, one way you can think about it, that this wind stress response is connected to what's happening onto a large scale response, whereas probably this one is not. Maybe I don't know how to explain this part. Don't know how to explain this part.
It could be that the upper level, the Walker circulation is responding to the warming already.
In this, there is no. This is a slab ocean
I
model.
know the upper level. That's the reason why the sign
Oh yeah.
going that way.
Yeah, means I think there is still some
It
feed.
means that there is anomalous water circulation responding to SST warming. But in the slab ocean case, there's no SST.
Yeah.
So there's essentially no Walker response.
The Walker response in the lower wind stress, yeah. So this is it. I think after that, I just some more extra figures, but
Good. It's making progress. Questions? Right?
I put everybody to sleep.
No, that's great. I think I would strongly recommend that you make some composite.
Composite.
Because the way you design the 6 farm, you can actually pick the see whether how the background state itself has a influence on the
Mhm.
response.
Okay.
Could be your responses very much depending on the background state itself.
It's possible. Means even I am thinking, but I think I just didn't get time to look at that.
So you made it pretty long. It's a 2 years each, right? You have 100 something.
I have like 300 years now. Okay, not 300 years, but
No, you have what is that?
so 110 plus
2.
110 plus one more of that. Ideally, it's like close to 300. I think we're going to make it still. I think we'll do another 20 years. I think 20, 30 years just to get the SST response is still not very. It's 85, as I said. I think it will come up.
Any questions? I think you're working on in the field. How many people already?
Yeah, it's.
How deep you see the temperature signal in the equatorial Pacific?
I will say that once more.
How deep you see the signal? You show
There's
pictures
a
for
picture
150
along the
meters,
equator.
right? So how deep does the temperature signal go? 200 meters?
Just show that picture along the equator you have.
Hmm.
There's a particular.
Yeah, but the thing is, this is an annual mean picture, you know.
That's fine.
Annual mean picture, so it's not significant. Statistically, it's not statistically significant,
Yeah.
but you can see that how deep it goes.
But still,
But what is interesting is the subsurface is definitely stronger than the surface.
It's definitely coming from the subsurface. It's the subsurface.
Definitely the warming signal you actually see is actually coming from the subsurface.
And the more important part is whether it is another line is whether it is coming from the Western Pacific, whether it is forced by the Western Pacific or not. We are seeing some evidence of it. We are also seeing it in a slab ocean model. So it is forced by that.
So it looks like the subsurface signal is around where the thermal line is.
exactly, that's what I want to see.
Yeah. About 100 meters.
This is actually very similar to how it should be, you know.
That's as I said. I mean, this just looks like an anemia signal.
Yeah. You might be actually interested. I don't-
Actually, that's kind of interesting, because like can think of know some interesting method of analysis if you read some of the that to read that stuff and
Yeah.
composite analysis.
So actually, if you look at this is what I'm showing here is on this one. This figure is what I've already shown you. This side. The other side is for the second year.
Well, that looks really weird.
That's how actually it is supposed to be. If you look at on the Eastern Pacific, you have a warming, but this is
But I think some of this could be, your Rossby wave coming back.
possible. You know, you have some, but
I mean,
what I'm saying here is that this, if you look in the literature, they do say that there's a cooling along this, there is a warming along that. It's because the thermocline shifts such a way. It shoals in one place and deepens in the other.
So the mean vector you're showing below is that the annual mean model simulated the mean current?
Yes, only the zonal.
Only the zonal current. So it's actually equatorial undercurrent.
Yes, those are in equatorial undercurrents.
So you're getting maybe a 10% reduction or something like that.
Yes. Yeah, around the maximas. Yeah, around. If you look at the maximas, yes,
10 centimeters.
yes.
Yeah, the only thing I can think of for now is actually if you can make a composite and just compositing according to the background state.
And see why it is caused in the
Taking
right.
out the strong year, trying to figure out
Which year- why is
which
what-
year the response is the strongest.
Okay. All right then.
Okay, great. So who's doing next week? Anybody know? Anybody check? Is that you? Are you?
So you want to close those things, right?
Yeah, just,
I need to look we have a website
wow.
and we transfer all
These are our windows.
So let's,
Well, let me see. We can just,
next week is May, April 6th.
April 6th is you?
Yeah.
Oh, okay.
Not next week.
Okay. So let's
Next
see
week.
who's the next week. Are we done? We're done,
Just
right?
just a second. I'll just
Okay.
close it and. So next week.
Let me see. I want to make sure it's.